Okay, so today we're going to take a look at stacks and queues. So stacks and queues is a advanced data structure. Okay, it's also called a abstract data structure. Just like the linked list, it has the ability to grow and shrink dynamically as the program is working. But it seems like it does a lot of what the linked list does. But what I want to talk about now is the advantages of hiding features, hiding data from programmers and from sort of the problem-solving process. So the fact that you can hide stuff, make stuff private, we can do that with variables, we can do that with data structures, we can do that with methods, we can make them public or private, hide them from inside or outside the class based on the design of what you're trying to construct as a programmer. Okay? The fancy word for this is the sort of interface that you're creating with your code. The abstract data structures often hide some of the features of the program itself from outside. So for example, in our linked list that we were working on, we made a method called findNode. But it was just a little private method within the class. The other methods inside the class used it, but if you were outside the class, you wouldn't know that this method called findNode existed. Okay? So we hid it. So we're going to see that when we develop some of these ADTs. And the three big ADTs that we're going to look at are the table, the stack, and the queue. The table specifically, we're going to look at something called a hash table in that. Okay, so if we imagine what the table would do, as a structure, okay, we would need to insert things into the table. We'd be able to delete things from the table. We should be able to search the table, and we should be able to output or print the table. Very similar to the linked list. Those are very common features. Okay? Now, a table can be something as simple as a 2D array, but it could also be something more complicated, and that's the one we're going to look at, is something a little more dynamic. But today we're going to focus on the stack. The stack object is a particular object that always adds things to the top and removes things from the top. So the best analogy is like a stack of dirty dishes, where when a new dirty dish comes in, you put it on the top of the stack, but when you go to wash a dish, you always pull it off the top of the stack. So this is what's called a LIFO structure. That's the acronym, which means the last one into the stack is the first one out of the stack. We're going to then later look at a different object that has a different structure to that. So for example, we could set the bottom of the stack to a null pointer so that that would indicate that we're at the bottom. Okay, so here's the animation. So when you add something to the stack, it always piles on the top of the stack. But when you remove things from the stack, you remove it from the top. So this one here at the very bottom of the stack was the first one in. It'll be the last one out. And this one, which was the last one in, is the first one out. Okay, and that's why it's called the LIFO structure. Okay, so that's the stack object. So here's what we're going to need to be able to do to create this thing. These are the methods we're going to write. Obviously, we'll write a constructor so we can build the stack. To add items to the stack, the word we're going to use in methods is push. And to remove it, we're going to use the word pop. So we push onto the stack, and we pop the stack to remove it. We'll also write a little method to just take a quick look at the top of the stack without actually removing it. We'll make a little isItEmpty method and one to determine the size of the stack. Okay? Now we will do this through inheritance of this big linked list class that we've been building. But as well, I will later show you an example of code how you could build the stack from scratch. Okay, so now I'm going to set this up in NetBeans. So I'm actually going to build a brand new project. I know you guys already have the project, so just indulge me for a sec. So I'm just going to make a Java application just called grade 12 code example 2014. Okay. And get that set up. So one of the things I showed you guys last time, and I'm going to put on this video, is this idea of organizing to the next level. The idea that we started our organization when we started learning about coding by organizing our code into methods. And methods are great, right? They allow you to dissect your code into separate parts. Once we got past that, then I also taught you how you could then also separate your code into classes. Okay? And classes is really the key to good programming as an object-oriented programming language, is building and designing objects and classes that really separate your logic into more usable chunks. Now, I think you guys are there. And now we're going to go to the next level, which is this idea of creating packages. Okay? That's the icon that NetBeans uses. It represents a package. Packages are ways to essentially separate your classes so that they can have similar names. In other programming languages, they are called namespaces. So you can have different namespaces and therefore use the same object of the same name within those different namespaces. But in Java, they call them packages. But at a simple level, it's just another way to organize your code. So as I said last time, the easy way to do this is just right-click and go New Package. And one I suggested was the one called Collections. Okay? And then I also suggested one called Databases. Okay? So when you create these packages in Java, they will be available in NetBeans, and it'll demonstrate them as little package icons. If they have nothing in them, the package will be gray. When it has a class in there, the package will be yellow, I guess, yellowish color. So again, what I suggested last time was take the linked list code that we worked on in our previous example and copy it into the collections package. So now your collections package will contain the linked list that we spent all that time working on in the last unit, and obviously for the linked list to work, it also needs our node class. So that's now part of our collections. And the other one I suggested we do is for the databases, take a copy of the file handler, the file handler class that we worked on in the unit before that. So this has kind of now collected some of our useful classes from the units. And again, we're going to kind of always use this project now to do our examples. So now, having that in place, I'm going to also rename this package. And what did we call it? I'm trying to remember exactly what we called it. I think I just called it something like main package or something like that. Something simple. Okay. And in there, I'm just going to rename this file just main class. Okay, so now I've added a level of organization to my code here so that I have packages to separate some of my stuff. And within the packages, I have classes which separate. Within the classes, I have methods and data structures. Much more organized. And now we can start building a stack object. Okay, so I'm going to new Java class. I'm going to call it the stack. Now as you build a new class, watch out right here which package it's being inserted into. That's an important distinction. So you can always shift it around, but now I can add the stack to my specific package. This now explains this line of code right here, what that line does. So that line that we often ignored now tells us which package this class is a part of. As well, when you use a class from a different package, it will import it based on that name. So the import statement will now include that. Okay, so now we're ready to start our stack. And here are some of the methods that we're going to need. We're going to need the constructor. We're going to need a public a public void push method that takes t data. And it's going to push it onto the stack. Now, the stack uses generics. So we're going to add the generic t up here to indicate that this stack will use generics to work. But we're not done yet. In addition to being generic, we are going to extend the linked list. Okay? So this top line of definition of the class will say that a stack is a linked list. Okay, so it maintains all the abilities of the linked list, and it deals with generics. Okay? So we will have a default constructor, so we can build the stack. We have a push method that will add objects to the top of the stack. We will have a public t-pop method that will remove, and let's just have it return null for now. We'll fill that in later. Remove objects from the stack. We'll have a public t-top method which doesn't remove objects from the stack, but looks at the object at the top of the stack. So just have it return null for now. So push pop top. We'll have a public Boolean is empty method, which for now we'll just have it return false. We'll do that in a second. And a public int size method that for now let's just have it return 0. Okay? So this is what I said we were going to do with our stack. That it would be very simple. It wouldn't have all the features of the linked list. We're going to hide most of them. Size is empty, top, pop, push, and a constructor. 6 methods. Okay? So it reduces what the linked list can do. Okay? So maybe I mentioned this word to you guys before. It's a kind of a buzzword in computer science. It's called skeuomorphism. Skeuomorphism is this idea that you take real-world objects and create software that mimics the real-world objects. So for example, you could get an app on your phone that looks like a 1970s rotary dial phone. Right? So it's trying to morph that environment through software. So again, kind of what we're doing in that is you're reducing the functionality to create an interface for the user that's something that they're maybe a little more comfortable with. Now that's not the case here with the stack. We're not reducing the functionality because programmers don't want to know what a linked list is. We're reducing it for specific programming purposes, that the stack's lack of abilities will create abilities for itself, that problem-solving things that we normally wouldn't think of. Now I'll get to that later. We can write this stack quite easily. The lines of code to fill in all these methods are actually very, very simple. To construct a stack, all I need to do is construct a linked list. What will be the line of code to do that? Well, it's the superclass. So I'm going to make a call to the superclass, and that's it. To construct a stack, construct the superclass. So it would go to the linked list class. Hang on. And it would find its default constructor, and it would run that code. And we've already done that. So that's all it takes to construct a stack. Now, we'll skip pushing and popping and top for a second. We'll get to those last. Is empty. Well, in our superclass, we actually already have an isEmpty method. So we can just return the call to super.isEmpty. Now this will prompt you that this seems like this is a override taking place. And it'll prompt you to add the override, which is fine. That's exactly what we're doing. We are overriding our superclass with our own method. It happens to be the same method, but that's what we're doing there. Okay? And size is a similar function. I returned super dot, and for that one, we called it length. So I've changed the name slightly between length and size, but it's the same idea. I just make a call to the superclass and pull out its method that does that already for us. Okay? So it's very simple. Now, the three methods that are left, push, pop, and top, okay? We have methods to do this as well, okay? But we have to be careful about how we implement them. Because think about our linked list. Our linked list, we drew it as a linear object, that it kind of always went this way. But now let's think of our stack as this way, okay? So when I push something onto the stack, it's always going to go here to the top, okay? And when I pop, so that's how I push things to the top. And when I pop things from the stack, I remove it from the top. That's how I pop things. Now, if we were to take this thing and turn it sideways, maybe you could see how we could implement it. And we could turn it, if we turned it this way, or if we turned it this way, it wouldn't matter, as long as we kept our method straight. So for example, if I turned it this way, we would always be inserting to the head, insert to the head, insert to the head, insert from the head. And when we popped it, we'd always be removing the head, removing the head, removing the head. Or if we turned it this way, we'd just be inserting to the tail, and removing the tail. So it doesn't matter. It doesn't matter which one we choose, as long as we as programmers keep it straight. So I say let's do it this way. Super dot insert tail of our data. If we always push it to the tail, we'll consider the tail the top of the list. And to pop it, we'll return super dot, is it delete? Sorry, delete tail. Now this will require a casting to data type T, because we're using generics, okay? So we're inserting to the tail and deleting the tail. Don't forget that you have to put that cast to T there. That way we always keep it straight, that we're always inserting to the front, or pardon me, to the back, and removing from the back. And again, the fact that this is a stack hides that this is taking place. We just push and pop as needed. So now, we also have a nice feature for top. We just returned super dot, and I believe we called it back. And again, this will have to be cast as a T, whoops, as a generic. But you may recall we wrote that method front and back, and all it does is look at what's at the front and back, and it doesn't actually remove it, which is exactly what top does. It just looks at what's at the top of the stack without removing it. So it's super, super simple. Each method just has one line of code. Each method essentially just uses what the superclass has. And now, if we go to main, this stack object is super simple to use. So let's just write a little sample here. Let's make a stack of data type, let's make it integers this time, called stack equals a new stack data type integer constructor. Okay? Now, this will require an import, okay, when you do this. But again, be careful with this, because just like the linked list, there is a built-in stack object in java.util. So once again, I'm teaching you something that you didn't have to learn, because you could have just used the default one. But instead, we're going to import it from our collections, collections.stack. That's our stack that we made our custom one. So that's the one we're going to import, okay? We're not going to use the one that's in the utility library, although I could show you what that one does, and you'd see basically some of the same stuff, okay? So now I can use this object, stack dot, I could push onto that, say a 50. I'll push three things on there, 50, 60, 70. And then I will pop the stack. Okay. And now I should output the stack. Okay, that's one line, that's one thing I didn't write. And actually, that reminds me, you guys should have stopped me. When we write a class, there's a couple methods that we should implement. Right? Remember I said that. What were those 4 methods? Clone. You're cheating. You're looking at your code. ToString is, no, not is empty. Destroy. Clone is empty, or clone, destroy, and there's one more. One more that stands to make things, no, we talked about ToString, to make things balanced between one thing and another. Equals, right. So let's write those. Let's do that for good measure. So let's write a public, whoops, public string ToString. Okay. So how do we write the ToString method? Well, we could use the superclass. We could return super.ToString. That makes life easy. But think about what the ToString method in linked list will do. If we look at what it did, and where is it? I got to find the crazy ToString method. Here it is. What it did is great. It does output the whole thing, but it uses the word list, which is okay. It's kind of a list, the stack object, but let's change it slightly. Let's add in front of this some words before that this is a stack, and then it'll say list, okay? So that's the only thing we'll add to ToString is that, just so that we know it's a stack, we're going to put the word stack plus super ToString, okay? And then we'll make the clone method. Oops. Which returns a clone, okay, of the current stack object. And again, we could just say return this. That would be, who remembers what that's called? That works. But there's a difference between making a true clone and making kind of a fake clone. Do you remember the words I used? Yeah, a reference. But there was 2 words I used to describe that. And I also used it in terms of searching. There was shallow and the opposite, deep. Deep. A deep copy versus a shallow copy. What's this one? Shallow, yeah. That's a shallow copy. But let's go with that. Let's cheat a little bit today. Just so, if we wanted to make a deep copy, we'd have to say like stack equals new stack, and we'd have to clone it that way. Or we could call super.clone. Maybe that would be a sort of, actually, why don't we do that? That's kind of a compromise. We'll just clone the superclass. Now, this again has got a problem because it's returning. You see there what it did? It kind of would need it to be a linked list. So it's 2 different objects. So cloning there is not quite as easy as you'd think. So let's just cheat again. Let's just put this. Let's make it a shallow copy. Let's be shallow. Let's be very shallow today. Okay? Now, what were the other ones? 2 more. We did ToString, we did clone, destroy. So void. And let's put final in there. Void, destroy. One of the other reasons, by the way, that you put final in a method, add that qualifier in there, is once you put the word final, it means that that method cannot be overridden. So you cannot, because now you'd think, oh, well, then all I got to do is go super.destroy. Okay? And you can actually see that. I can't zoom in on it, but if you guys look at the light bulb, it says destroy cannot override destroy in linked list. The overridden method is final. Shoot, I can't do that, okay? I can't destroy, I can't override a method that is already marked as final, okay? So be careful with destroy and that adding that final keyword. It can sometimes throw your logic off a little bit. So you know what? Let's not write that one. Okay? We'll leave that one off the list. So remember I said those 4 methods are a good idea to implement, but not always, right? Sometimes maybe you don't. And we'll also skip equals. We'll skip equals at this point. Okay, so we've got a very simple stack class. Let's use it. Sout stack. So we're going to build the stack. We're going to push 3 items onto it. We're going to pop it once and then output it. Before you run your code, what should come out? What should be on the stack? 50, 60, yeah. Because 70 was the last thing put on, but it's also the first thing popped off the stack. So let's see. 50, 60, good. So we got 50, 60 happening there. Now as well, when we popped it, we returned that. So really we could have outputted that pop. So let's do that. Let's add a little output to that. So when we pop it, it's returning it. So we could actually see, make sure that the 70 is actually being popped off there before we print the stack. We'll run that. Yep, the 70 is showing up there. So it popped it, and then the stack looked like that. So let's do that, those 2 lines 2 more times. We'll pop it and output it, pop it and output it. Okay? And if we take a look at our thing, we'll see it's working. So the 70 was popped, then the 60 was popped, then the 50 was popped, and it kept track that it was an empty list. That worked too. So the stack object has a very simple implementation that you can just push and pop and a few other little features. But what good is it? I haven't proven what good this thing is, like how it could be more useful than a linked list in certain programming problems. Okay? Well, it can. I mean, think of it this way. You guys know about classes, you know about arrays, you know about linked lists. You got a very deep knowledge of dynamic memory management in a computer programming environment. But if I asked you to write a simple program to add 2 numbers together, would you write like a linked list and classes and all that? No, you would probably just use something simple like a couple integers and just do it. You wouldn't need all the functionality that you're aware of. Based on the problem, you would have kind of fit the tool to that particular problem. So the stack fits some problems. Okay? Okay, so let me show you guys a couple more things about stacks just on the presentation side. Okay, so we were able to do what I said we could do. We can create it, push, pop, top is empty in size. We got that done. Okay? What I'm showing to you now is we didn't code this, but this is, I'm just going to dim the lights for a bit here. Sorry, grade 11s. This is what it would look like if we didn't use inheritance. We could create a node, and I would maybe change the name to stack node, and it would be very similar to the linked list node, except I wouldn't need a double reference. So I could just have a reference to the next node. So it's simpler. Create a constructor, override the toString method. Then I would make a stack object. The stack object would just need a reference to the top. It wouldn't need, for example, like in other words, I wouldn't need head and tail. I could maybe just keep track of the top and the length. I could build my constructor. I could write the size method, return the length. I could write an isEmpty method that just checks to see if the length is 0. And the toString method would be, again, very similar code where I just loop through and output it. Again, remember, I'm not using inheritance here. The push method would also be very simple. I'd create a new node, assign its data, which, by the way, I could have done in one method there, but I didn't write an overridden constructor for that class. If it's empty, I would set it to the top. Otherwise, I would just set the top to that node and increase the length. So all the logic got simpler, way simpler. Pop, same thing, much simpler logic. If it's empty, return null. Otherwise, reduce the length, give me the data, move the top to the next reference, and return the data. Very, very simple code. Top, also very simple. So in the notes is an example of how you could write a stack object from scratch without using inheritance, okay? And then the code that would test it, okay? And then the linked list object is the one that I just did that we did together, okay? And there's even an example in the code of that, but we just typed that in, so I'm just going to skip through that. Is it going to work now? There we go. Okay, so finally, why would I need this thing? Okay? Well, there are several reasons for doing this. Okay? As a tool, it's simpler, so it can work on some problems. For example, text parsing. So being able to take text and read through it, which is very common in programming sometimes. A lot of you guys did that for your files problems, where you'd scroll through the text and analyze the text that was coming in. Believe it or not, that's actually how methods work. Methods work on something called the runtime stack, which is essentially how the computer keeps track of method calls. So when it calls a method, it then puts the next method call on top of it on the stack. So say you had this program that said run, and then run called like start, middle, end, and it would keep track of the method calls on something it calls the runtime stack that basically does that. It pops and pushes things onto the stack accordingly, okay? But the one I wanted to show you guys is an interesting one, okay? It's a way to do math that you are not familiar with, but it's the way the computer does, and it uses brackets and braces. So here's a piece of math, okay? Forget computer science. This is just basic math, although you have to change that to multiplication, and that's a division. That's a problem, right? That's a math problem. And you could use BEDMOS to solve this. But the question is there any mistakes in the brackets up there? You look at that. Now, you are just scanning that with your eyes and your brain logic right now. But what I'm going to propose is an algorithm that scans this mathematical equation to make sure that the brackets are nested properly. Which, by the way, is what programs like NetBeans do, right? To make sure your brackets aren't off. But how can we do that? How can we scan this? Well, here's what I'm going to propose. We start on the left and we move towards the right. We will, when we encounter a left bracket or brace or parentheses, we'll put it on the stack. So we'll keep track of that on the stack. When we encounter a right brace or a right parentheses, we will then pop the stack. Okay? And if the pop matches, the two brackets match, then we're okay. But if they don't match, we have an error. Okay? If the stack is empty and we're out of input, then again we have an error. But if the input is finished, in other words, we get through all of these characters, and the stack still has something on it, then again we have an error. Now, if you have been taking a minute to look at that equation, there is no errors in it. Okay? It is fine. But let's try our algorithm and see if it works. So I start my algorithm off and I encounter my first character. It's a bracket. So I'm going to put it on the stack. Okay? Then my next character is a 5. I'm going to skip over that. And then an operation, multiplication. And then I encounter another opening bracket. So I put it on the stack. And then I encounter an 8 and a minus and a 2. And then I encounter a right bracket. So according to my algorithm, when I encounter a right bracket, I look at the top of the stack, and if they match, they're the same type of brackets, curly, round bracket, success, I pop the stack. And now I continue. I encounter a right bracket. Oh, it matches, I pop the stack. Keep reading. Oh, left bracket, add it to the stack. Left bracket, add it to the stack. Keep reading. Left bracket, add it to the stack. Keep reading. Right bracket, do they match? Yep, pop the stack. Right bracket, do they match? Yep, pop the stack. Keep reading. Left bracket, add it to the stack. Keep reading. Right bracket, they match, pop the stack. Right bracket, they match, pop the stack. I'm out of input. My stack is empty. I have a successful equation here. The stack is a simple way of, for example, parsing through that text and checking for errors. If you were to write an algorithm to do this without stacks and queues, or pardon, without a stack, with just the linked list, you might have too many features of the linked list to maybe accurately do that. It's simpler. It's a simpler algorithm with a simpler data structure like the stack. Okay? Now, let's go up another level. Since we're talking about math, now let me teach you the way the computer does math. Okay? This is the way you're familiar with math. When you see an equation like this, you know how it works. You know BEDMOS says do the brackets first, then do the multiplication, and then do the addition last. And we write it in that format to do that. Why did we put the brackets there in regular math? Why? To override the BEDMOS, right? So that you know that still gets done first. But to a computer, it can write this in a different way where it does not need brackets. This format that you guys are used to, and by the way, most math teachers won't know this because they don't need to know this, is it's known as infix notation. So that's called infix notation. What I'm going to teach you are two other ways to write it called prefix notation and postfix notation. The word pre before and the word post after kind of give clues as to how they work. But I'm going to blow you guys' minds today in how math is actually done. So you can write any equation without brackets, and it'll still work. So we'll start with a simple one. 6 minus 1. Okay? And actually, let me launch some notes here as well. I want to make a copy of this. So my apologies. I'm just going to... Okay. So to be clear, an operator performs an operation on two operands. If you think of it in computer science terms, it's like this thing is a method called minus that requires two parameters. And it returns a value. Okay? So an operator performs an operation on two operands. Yeah? But who says we have to write it that way in math? Who says we have to say this operation, this operand, like we can change the order if we want. Why couldn't we write it like this? Okay? Now what does that mean? Well, it could mean the same thing. This is the operator, and these are the two operands. Now the order would matter, but we could also write it like this. Or we could write it like this. Or like this. As opposed to the way we're used to writing it, which is like this. So here are four alternate ways to write the same operation. But what's the advantage to that? Well, there is an advantage to that. Okay? So in... where'd my mouse go? The computer is so slow today. In prefix notation, it's written like this. That's called prefix notation. Okay? In postfix notation, it's written like that. And we know the one we're aware of is called infix notation. Okay? So you can see here that the way it's switched up is fairly simple. Pre means before. Post means after. Okay? But that was a really simple one. Let's try one that's a little more complex. Okay? That's infix. Okay? That's an infix notation. That's the way you guys are aware of it. In math, maybe you'd write it the 2 over here, but it'd be the same idea, right? In prefix notation, it's written this way. Oh, sorry, one more. That's prefix. Now that's really bizarre to know that this and this are the same equation. But how we evaluate it is kind of important, okay? The way it works is using stacks, okay? So the way it works with stacks is you start here and you start reading. And when you encounter an operator, put it on the stack. So, okay, that's an operator. I'll put it on the stack. That's an operator. I'll put it on the stack. Okay? When I encounter two operands, I pop the stack and perform the operation. So 4 and 3, operation plus. What's 4 plus 3? Really? The answer, since this was now just popped off the stack, the answer is placed on the stack. And now I read the next one, 2. Oh, wait, I've got two operators, or sorry, two operands, pop them and the operation and put the answer on the stack. 7 times 2 is 14. And I have no more input and I'm done. So we'll see how this works in a minute, but this idea of prefix and postfix notation actually allows you to write math equations without brackets. Now, hang on. Where is it? Did I shut it off? I guess I did. Oops. So here it is on the slide again. So there's the infix notation. That's prefix. This is postfix. And here's another one, prefix, postfix. So it allows you to write math equations without brackets. Now, believe it or not, I'm going to teach you guys how to do this. You're going to be able to write these equations. I'll make you a really hard one, and eventually you'll get it. So let me show you the little animation I did to come up with this. And then we got a wrap for today, and I realize I went kind of long today. But I get excited about this stuff. I do. Okay. Here's the example. Oh, we're out of time. That's for tomorrow.